Right. So I guess we can start with a question to Junwu that we talk about the facts of like bosons. Please.
Okay, thank you. Well, since I'm the last speaker of this week, I would take the opportunity to thank the organizers, Luca, Pierre, and GP, for inviting me, and also like to the administrators for putting up with us during the workshop. So today I'll be telling you about the defects of light bosons, and so I would like to tell you something about collective effects in dark matter, and in especially for light dark matter. And the idea behind these studies is the fact that the universe as we know it is not empty. And in particular, there are a lot of like dark matter, especially if the dark matter is light. There's a lot of standard model medium, and some of the standard medium is very dense. And hence, a lot of interesting behaviors can happen in this medium. And to quote Anderson, more is different. And we'll see this also happens in dark matter. So I won't be able to go through like all kinds of collective effects. So today I will be restricting myself to talking about only these objects which are known as topological defects, mainly because they can stay for, once they are produced, they can stay through the evolution of the universe due to the protection of topology. So I'm sure like everyone is familiar with the monopoles. But like today, I will mainly be telling you about some of these codimensional two objects, the strings, and Axion strings. I will say something about photon strings, and then like some dark photon strings, and how these topological defects can give you incredible signals, and also sometimes make you very sad about in certain conditions. I will see how they occur. All right, so since we'll be talking a lot about strings, let me first say something about where they come from. And the most well-known way where like these topological defects, especially strings, come from is known as the Kibble mechanism, where all that required is that the universe was once hot enough, or the energy density in the universe was ever large enough, such that the universe has some phase transition. In this case, a U1 phase transition happening in the early universe. So in the very early universe, the Hubble patch is quite tiny. And at the time of the phase transition, all of these different patches choose their direction randomly in the Mexican Head potential. As the universe expands, of course, these patches come into causal contact. And there are regions, for example, here, where there's a non-trivial winding of the field, which goes from 0 to 2 pi, and that will be the regions where topological defects like a string will form. So after they form, these strings will interact with each other, and they can cross each other and form loops. These loops will oscillate and dissipate, which cap the string network in what is known as a scaling solution. And the scaling solution features order 1 strings per Hubble patch. Okay, so Marco is an expert on this, of course. Since the seminal paper we have known about this logarithmic scaling violation, where instead of having 1 strings per Hubble patch, we can have logarithmic many of these them like in a Hubble patch. Here, like we'll be introducing the first free parameter in the discussion. I'm not as sophisticated to run these simulations, so I will just take like the number of string per Hubble patch as a free parameter, which somehow can run from 1 to maybe 100. Okay. So I told you about how these defects are produced. So why do we care, right? Like, why do we want to think about defects? Well, because they are special, and in particular, even sometimes one topological defects will offer us informations about quantization that you will never be able to find elsewhere. And classic example is the magnetic monopole, right? Dirac realize this Dirac quantization condition from the quantization of angular momentum. And it is like, so if you see a single monopole in the universe and measure its magnetic charge from this relation, you will automatically infer that the electron will have unit charge. So you get a very strong information about charge quantization this way from one single magnetic object. So today I will be telling you something that does the same thing, which are these cosmic axion strings or X-verse strings. So, so this object is a string, and the start means like the string is like a perpendicular to the surface going into the board. And around the string, in particular for axion string, as you rotate from 0 to 2 pi around the string, the axion field goes from 0 to 2 pi Fa. Okay? And this winding is basically what defines this topological defect. The second thing we know is axions can couple to photons, and their coupling usually come from a one loop diagram, where like proportional to the phi structure constant times this anomaly coefficient. We already heard a lot about this anomaly coefficient from Mario's talk. For today's talk, we'll just say like this is the sum of a bunch of charges in electric charges and PQ charges of the PQ quarks, or maybe some leptons. And this anomaly coefficient A is always an integer ratio if there's charge quantization. So with this coupling, a phenomenon that is very intriguing is, and first discovered by Pierre in 1992, is that if you send a circular polarized light through axion background, okay, the different circular polarized light will pick up different phase. And the amount of phase that they pick up is independent of the exact path that this photon has taken, but just on the initial and the final value of the axion field. Okay, so this is a topological effect coming from the fact that the coupling is a derivative coupling. So that's all the ingredients we'll need. Now let's see what happens to axion string. Okay, so to do that, I will walk you through three figures. So the first one, I have axion string, which is going through the board, and I'm sending a photon in a circle around the axion string. Okay, as the photon is going around the axion string, the axion field would change from 0 to 2 pi f, and as a result, this photon, which might be linearly polarized, will have a polarization direction which start to rotate. And by the time you get to the point it start with, the polarization has rotated by 2 pi Fa over 2 pi Fa times the A alpha. So this is just plus minus A alpha, where the plus minus sign depends on which orientation like the photon is going. Okay, so this effect is a topological effect, and this phase that we're seeing is a barrier phase. Okay, so this certainly is not very realistic. I'm never sending a photon around like a string somewhere in the universe. But since it's a topological effect, we can do whatever we want with the geometry, right? So I can take these two photons and tear them apart. So now I have two photon passes on the two sides of the axion string, coming from minus infinity to plus infinity, for example. So these two passes, due to symmetry, would pick up the same amount of phase in absolute value. However, you also know if you take this pass minus that pass, you form a circle, and every circle you get A alpha, which means that each delta phi is A alpha over 2, just the sign is different from the two passes. Okay, so this is already very realistic because this is exactly what happens in the CMB, right? So in the CMB, you have photons coming from very far away at the time of last scattering, going through the axion string network and enter your detector. So we'll see how this can be measured. The third picture I'm going to use is with axion string loops. So this red circle is axion string loop. And now I'm looking at the two photon trajectories, 1 and 2. Okay. So the photon 2 is like outside the string loop. And using topology, I can take this all the way to infinity. And certainly it's now going to be affected by the string loop. So delta phi 2 equal to 0. Well, the phase rotation of photon 1 differs from photon 2 by A alpha, since you can take like these photon passes and close a circle like at very far away. So, which means any photon which goes through the loop would either pick up A alpha or minus, plus or minus A alpha, depending on the orientation of the string. Okay. So that's basically the effect. Yes. Yeah. Oh, right here. Yeah. No, that phase is changed by A alpha because now you have a topological defect. Yeah. Yeah, right. When you have a topological defect, it's like it's not single valued. So the delta A is non-zero. Oops, sorry. Keep going.
No. It looks like.
No, like when you have like a topological defect, it goes from 0 to 2 pi. Yeah. Right. Well, the reason is because like when you have a topological defect, it is not single value. So like even if you are at the same point, depending on how many times you wind around the topological defect, the phase would change by integer numbers. Yeah. Okay. Yeah, that's what the equation says. Anyway, other questions? I cannot get it to work. So. This way?
Yeah.
Oh, okay. Okay. No question? Okay. All right. Oh. Okay. Thank you. Thank you. Yeah. All right. If there are no more questions, we can go to the CMB polarizations that we measure, right? So in CMB, we measure two types of polarization patterns, the E mode and the B mode, right? So the E mode look like this, and the B mode is rotated by with respect to the E mode. So now let's see what they do when we have the Axion string. So if I send an E mode through like an Axion string loop, each single polarization vector is going to rotate in the same direction by the same amount. So it contains some part of the B mode, right? Which means I can do the following. I can take the E mode map I measure, I can take the B mode map I measure, and reconstruct this phi field, which comes from the polarization rotation. So if I do a quadratic estimator of EBB, I can extract this phi-phi correlation. And that's the correlation we can compute with the string network. So I'm not going to bore you with the details. This is the result. Plotted in terms of the two free parameters we used. The C, which as you remember is the number of string per Hubble patch, and A is the anomalistic coefficient. Okay, so since this is this is coming from some charged matter which is similar to what standard model has to offer, then this anomalistic coefficient should be at least like an integer ratio of integer multiple of 1/9, or more likely like an integer multiple of 1/3. Okay, so anywhere to the right of this line is an interesting parameter space. Of course, C has to be bigger than 1, so that's basically the regional parameter space we are interested in. And what you can see already is that the projection says the Planck 2015 data is somewhere exactly in the middle. So this analysis is very imminent. And if we look at things like Simon's observatory of S4, it will cover all the interesting parameter space in the next 10 to 20 years. Okay, so since our paper, there has been many interesting follow-ups, and I would just want to highlight the last two, which was done by Liang and the Simone's group, like in Berkeley, where they studied basically like the searches for these objects with more sophisticated cosmological analysis. So in this paper, they ran like a 4 quadratic estimator analysis, and they basically confirmed the projections that we made. And in this paper, they took on the challenge to look for single individual strings. And the reason we want to do that is that the phase difference between the two edges of the strings tells me about the anomaly coefficient. And only doing that type of analysis will we be able to like measure this integer ratio that we want to get, okay, for axion physics. So I'm showing you some figures here. So this one is basically the figure that we made, where like there's no noise at all. And what you are seeing here is a string which separates the two regions with a different polarization angle. So if you look at this figure, you will say like it's very easy to find this object. This is what happens if you put in noise, right? So and this is you can still see like by eye that there are loops in the data given where like there is a circle here and there is another circle here, which are string edges. Okay, extracting this information from real data is very hard, but in this I would say very exciting work, they showed that with future CME missions, they can do a measurement and distinguish if the anomaly coefficient is 2/3 or 1/3. Okay, which says if we ever see like the string network in the future missions, we will be able to measure this quantity directly. And I think it's very interesting. Okay, any questions about this? Yeah. I think like for this, like you can do 2 sigma like with CMHD. Yeah. So for active strings, so these will be like very light axions, massless axions usually. Hmm?
So it depends on the mass.
No, it's independent on the mass. The effect is independent on the mass, independent of FA. But like if the mass or FA is too large, then the string would contain too much energy density as well already be excluded. Yeah. Yeah. Huh? Oh, so like if you think it's like some PQ quarks, right? Like so the charge would be like 1/3 square times 3 like 3 colors, so that will be 1/3. QA times it's like Planck charges, yeah. Oh yeah, definitely. Yeah. It's just like this is the limit they can push it. But like if it is 1/3 or 1/9, it's very hard to distinguish. Yeah, we don't have the precision yet. Thank you for the question. All right. Okay, so that's all about axion strings. So now let me move on to talk about dark photon strings. So the question is, okay, so like we talked about axion strings, what about dark photons? And I need to apologize since this is, Luca wants me to talk about axions. But I think this is pretty cool and I hope I don't disappoint you. So in order to talk about dark photon strings, I will actually first talk about photon strings. Especially in the context of a superconductor. So here, like I will be giving you a short summary of what we discovered, and then we realized that the condensed matter people know these things like 60 years ago. Okay, so here, like I will be talking about the superconductor phenomenology with basically the Landau-Ginzburg model, having in mind that this phi field basically is the field of the Cooper pair, which is a pair of 2 electrons. Okay. So with the Landau-Ginzburg model, there are 2 different types of superconductors. There's the type 1, which is when this quartic is smaller than the electric charge. Oh, sorry, like one thing I need to say, like for all of these discussion, I'm taking the Fermi velocity to be 1, so that I'm not keeping track of the velocities, just like we take C equal to 1 in DSM physics. So yeah, so like in the limit where like the quartic is smaller than E squared, it means like the coherence length is longer than the magnetic penetration depth. So in this case, it's the type 1 superconductor, and it has 2 phases. At a very low magnetic field strength, you have the Meissner phase, where all the magnetic field is expelled by the superconductor, right? Well, as you continue to increase the magnetic field, at some point the superconductor stop working and the B field penetrate everywhere and the superconductivity is lost. Okay, so that's basically the 2 phases which exist as I change the magnetic field strength. In the case of type 2, the situation becomes more interesting. So like in this limit, what happens is you still have these 2 phases, okay, but like the critical field 1 and 2 are not the same. So below BC1, you still have the Meissner phase, and above like this field strength, you still have the phase where like magnetic field lines everywhere. But if like lambda is bigger than E squared, then there is a gap in between. What happens in between is a very interesting phase of matter, and that is first discovered by Abakusov in 1957, and hence it is called the Abakusov vortex or lattice. Okay? So here, like you are looking at a single Abakusov vortex, which features a core of the order parameter phi, and a B field profile which looks like this. Okay, so in superconductor, if there's no magnetic field, then phi over V equal to 1. Okay, the symmetry is broken, and the B field is equal to 0. But inside the vortex, within a very small region, the phi will go down to 0, and the magnetic field strength will grow like inside the vortex line. So the core of the string is set by the mass of the phi, and it is tiny when lambda is large, while over a much larger range of length scales, there is magnetic field which has this profile. And the vortex is defined by this constant that like the integral of a mu integrated around a circle around this vortex core is equal to 1 magnetic flux quanta phi naught, which is 2 pi over 2e. So here the 2 comes from the fact that the Cooper pair has charge 2. And the important thing you should remember, and it is probably the most important message when you are looking at this magnetic flux, is that the flux is inverse proportional to the electric charge, telling you that what you are seeing here is a magnetic object. And when you are taking this charge to 0, the flux goes to infinity, which means this object does not decouple. Okay, and we'll see why it matters very much. Okay, so in condensed matter systems, like if you put in some like non-zero magnetic field, then what you get is this lattice solution where there are a bunch of vortex lines like equally spaced from each other, where the spacing is set by the magnetic field strength. And this is the phase, which is the ground state above BC1. Okay, so it took 10 years, and then like Galecko realized that this phase transition between like this phase where like the phi is a constant and B is constant to the phase which contains this vortices is actually a second order phase transition. And the way it works is shown in this figure, and let me walk you through it. So let's say like you have a tiny bit of magnetic field perturbation at this point, which makes the B field a little bit larger. Okay? So from this equation, what you will see is that the phi field wants to be a little bit smaller in the same region when the B field increases. And phi times G is the mass of the photon, which means that the photon is lighter in this regime, And through Meissner effect, you know that the magnetic flux wants to be in regions where the photon mass is smaller. So the flux will continue to cluster in this region. The B field will increase. The phi will continue to go down. The B field will increase until this runaway process leads to the formation of a vortex. Through all of these dynamics, all you are trying to counter, all this growth of the B field is going to counter is the changing gradient energy. And as a result, you never need to really see the fact that this phi field is extremely heavy. Okay, so that's basically what was discovered by Galeko, who understood this instability, which makes this phase transition second order. Okay, so one comment: this phi field do not need to be a fundamental degree of freedom, and as we know, like it's a Cooper pair, right? Like it's a pair of electrons in this case. So you do not need to introduce a fundamental degree of freedom as the Higgs. And such a phenomenon was actually like already in use by Eric Adelberger, and Andrei Gruzanov to relax the photon mass limit from galactic B field by assuming like there are these vortices inside the galaxies. Okay, so if you are interested, I think this is a very interesting paper. Okay, so that's all about the photon vortices. And I introduced this material like in the context of a superconductor. But what I will show you is that the same dynamics actually occur for any dark U1 when you want to pump energy into this dark U1. So what I will show you is if you try to produce dark photon dark matter, for example, or dark photon superradiance, or any way you want to pump energy density into this field, vortex form, and things change very dramatically. So the first thing that I'm showing you is a simulation done by Will East, where what he's simulating is the growth of the superradiance cloud around a spinning black hole. So here, like the details doesn't matter. All you need to know is that in this process, the electromagnetic field of the dark photon is increasing as a function of time. So let me run it again. Sorry. So what you're seeing is as this field is continuing to grow at some point, there is a string, which is a green line. So let's please. Okay, so which showed up. And after it showed up, it was pushed around by the background gauge field until it gets back to the black hole because of gravitational attraction. Okay, and string tension. So in this process, the strings form inside this fluid and takes away all the energy that is inside the background field. Okay, so you can see this better in this figures. So what you're seeing is that as I'm increasing gradually the electromagnetic field in this medium, at some point there's a jump of the phi field and a vortex formed. Basically here, like phi over v equal to 0. And then after the formation, like there is some complicated evolution that I will give you more intuition about later. So at this t equal to 0, this is how the field structures look like. You see a vortex loop which formed, and in the both in the amplitude of the radial mode, and also in the phase. So here, like you see a vortex, which is basically the location where the angular phase goes from 0 to 2 pi. Okay, so this is a vortex, and it formed as a loop. Okay, so what happens afterwards? As I already alluded to, the formation of the vortices kills any background dark photon field you produce. And this is how it works. Let me walk through this figure too. So what you are seeing here is a vortex line, which is perpendicular to the surface. Okay, so the string is going this way, and the circle represents the region where the magnetic flux is striding through. So it's like a solenoid. Well, the background field is the blue shaded region, which here, for example, I'm putting an electric field in the y direction. Okay, so the solenoid, let's say, is moving in the x direction. What you can compute from is the A vector outside this solenoid, and from which you can get to the electric field that is around this moving solenoid. Okay? You can do this computation, or you can just see like the figure I drew. This is how the electric field look like, the orange line. And the electric field is dipole field in 2 dimensions, with a dipole moment, which is per unit length, V over G dark. And here you see it again. G dark is in the denominator, which tells you about the non-decoupling of this object. Okay, it's a magnetic object. So what happens? Well, if I turn on a background electric field, this electric dipole wants to be large such that it will minimize this dipole energy E dot D, right? And what it means is that this vortex line will be accelerated in the direction that is perpendicular to the field you set up. Okay, so this is very analogous to the Hall effect. If you have a perpendicular electric field, the current goes perpendicular, in the perpendicular direction to the electric field. And when does this stop? Well, this stops when this electric field, which is pushing on this vortex line, is no longer strong enough against the string tension, right? So by equaling these 2 quantities, you can get the first critical field back, which goes as E dark of V squared times V squared. And this is a very small electric field. And to show you that, let me show you this simulation result. So here is a simulation of dark photon, dark matter, where like vortex has formed in this configuration once the critical field is reached. And then, which is basically here at t equal to 0. So the field has grown and the vortex formed at this point. After that, the vortex takes away almost all of the energy coming from off the background field, while the background field slowly decrease to the point where it approaches PC1. Okay, so what this plot is telling you is, as long as the string network is still around, you will never be able to produce dark photon, dark matter ever again, and the energy density is gone. Okay, and all of these mechanisms apply to all dark photon, dark matter production mechanisms, where the dark photon comes from a compact group. Okay, so what are the implications? Well, first, maybe we don't have dark photon, dark matter. At least it's not a U1. Secondly, in the case of the superradiance, it is actually very interesting phenomenology, because now, like, you can use the superradiance cloud as a string factory, right? You are producing these vortex, they can interact with each other and get injected from the black hole region. And you can get a string Bose-Nova. All these strings will come out. They will come out in such great quantities, even if we are a kiloparsec or 10 kiloparsec away from the black hole, which is shedding out these strings. We'll be able to get a couple like every year on the Earth. And we are with the Anson's group and his 2 students, especially, we are studying the phenomenological implications when these objects fly through the Earth, and especially fly through the gravitational wave detectors. It will look like a glitch. It's very funny. And we are trying to understand how well we can look for them. No. The reason is because the gauge, like in order to do this, you require this non-decoupling, and also you require the fact that the gauge field can push on the strings and letting them go. Okay. Questions? Yes. What? What sets the coherence scale of what? Of the string or of the field? So So here, like, basically, like, as you are producing the dark photon dark matter, you are producing K modes, which are order MA. And that's the simulation that we ran. And in this case, like the coherence scale is roughly like 1 MA. But like, as you see, like this is actually like a really, really tiny amount of time after the string has formed. So they actually evolve like very dramatically. And such a process is called the melting phase transition in condensed matter language. And it is something that I think people have been struggling with for a very, very long time. And yeah, actually they are interested in what we did. Anyway, yeah. Yeah. So yeah. So like in the case of the superconductor, like all you have is a magnetic field. So the simulation we ran, we are mostly trying to understand like if having background electric field changes the story or not. And the answer is not. So like in the Landau-Ginsburg like discussion, right? They are working with a free energy. So there's only magnetic field, and there's pretty much no time dependence in that analysis. But so we ran this simulation to show that all of these differences doesn't change like the result. So like yeah, so this is something that yeah, thank you for the question. Like this is something I forgot to say. Like in the limits where so the Stuckelberg limit corresponds to the limit where like the quartic over G dark is going to infinity, and that's the type 2 regime. In the case of type 1, basically the Higgs is very, very light, lighter than a dark photon. So like in that case, you're already killed by like all this cooling bond. Yeah. Good. Cool. Thank you. Yeah. Yeah. So I think like here, like yeah, like you need like enough fluxes within 1/MA of length. So 1/MA is basically like doing the same thing as the screening length. Yeah. Yeah. Okay. So okay, so I guess I still have some time. Okay, so then like in the last little bit of time, I will talk about axion domain walls and their dynamics. So here, so in the first part, I basically said like these free dangling axion strings can give you interesting signatures. In the second part, we talk about when we pump energy into the field has like a react to itself. The dark photon reacts to itself and the strings form. So in this case, we are talking about standard model medium and how it can affect the properties of the light field. Okay, so the motivation for this comes from actually like my frustration with all of these experiments, and where I was trying to like Anson and I were trying to understand if it make like despite all the model building like complications and frustrations and whatever, like does it make any sense to look into this part of a parameter space? Or like it's all just excluded. So what we discovered back then was the fact that if you go to an object with a finite density, then this finite density effect, just like a finite temperature effect, changes the axion potential. So the mass you can do just look at the set of equations, but the important understanding is that when you raise the temperature or when you raise the density and the chemical potential, you make the axion potential flatter. So the change when you raise temperature is well known, right? At high temperature, the QC axion potential just go away. Well, at finite density, the same thing happened. And here is the consequence. So for a QC axion, as you increase the density, making the density denser and denser, the potential will get smaller and smaller. At infinite density, you recover basically a flat potential for the QCD axion. However, if you are living to the left of the QCD axion line, as you are increasing the density, the potential was already smaller. So now it not only get flatter, but as you continue to increase density, it actually flips over. So now what you get is inside these dense large stellar objects, the axion is actually here at the theta equal to pi instead of at theta equal to 0. So in this paper that we wrote back then, we basically said it is impossible for the Earth, certainly, or the Sun to be in a system where theta equal to pi. So the Sun, for example, have all kinds of nuclear reactions, which give me like high energy neutrinos, especially the beryllium neutrino, which we can predict from nuclear theory, and certainly will change by a huge amount if the theta is pi inside the Sun. So with that, we concluded that all of this parameter space is certainly not allowed. And then we decided that there are two different type of behaviors outside this region where theta equal to pi. So, so in this part of our parameter space, to the left of this this point, where like this line basically tells you like how big is the object. If the actual mass is very light compared to 1 over r, then outside of the object you have a slow decay of this theta from theta equal to pi to theta equal to 0. Okay. Well, if you are to the right of this line, for example, for the neutron star, then the profile of which interpolate from theta equal to pi inside the star and the theta equal to 0 in vacuum is the same-ish domain war-like structure. Okay. So since then, we convinced some people in LIGO to search for if like we have evidence for this case, where if you have if both of the neutron star have some fluffy field profile outside, the overlapping field profile exert a force between each other, and hence it will change the gravitational wave waveforms in neutron star mergers. And certainly there's no such evidence, and hence like this regional parameter space is excluded. So I want to also highlight this recent work by Andy Weiler's group, Habisera and I think students, where they demonstrated that not only like do we need to rely on these chemical reactions being different in different stellar objects, but the fact that the white dwarf hasn't collapsed at all already places a constraint on the region of the parameter space. So all of this is already excluded just because they are white dwarfs. So we are closing this region. And this type of constraint applies to all kinds of cases that land you in the region. So these kind of things like apply to all the different ways that land you into this regional parameter space. It's independent of whether you want to do some tuning to get yourself there or using some model building to get yourself there in that regional parameter space. So in the last few minutes, I want to say something about expanding bubbles. And this paper I also wrote says where we talk about localized bubbles. Okay, so all of the discussion I had before was about static localized objects, neutron stars, stars. We are thinking about a static domain wall that is wrapping the star. In many models, like the situation actually gets worse when you think about dynamical processes. For example, a supernova. So supernova is one of these processes where the density in the core continues to grow, and it grows past some threshold, and the thing collapses into a neutron star launching shock waves outside. If there is this domain world structure of axions outside this dense object, then the shock wave is going to take them out. And well, Lorenzo is not here, but I want to thank him for the inspiration. So like you are seeing, so this domain will be taken out by the shock wave, and this object will go out to a much larger of regions. And crazy things is happening in this region because all of this region has theta equal to pi. And certainly we are not seeing that. And here are some parameter space where this bubble can be like sizes of main sequence stars, so like second size, or even like 100 like second bubbles. So we are definitely not seeing these objects, and hence I think like all of this parameter space is not valid. So in particular, it is really, really pathological for the ZN model because in that case, no matter at what number density or energy density of normal matter, the theta equal to 0 is always not the true minimum, and the other minimums wants to expand into that, and this bubble will go indefinitely. So that's all I want to say about all of these collective phenomena, topological defects. We talked about the axion strings and how it leaves this, I think, a very interesting signal, like in the CMB polarization map. We talked about how the formation of the dark photon string is inevitable when you are trying to increase pump energy into the dark photon field, and how that cleans up like all the energy density you try to pump into there, and some of the signatures that this can lead to. I said something about this region of parameter space to the left of the QC axion line, and why, in my mind, we shouldn't go there. And in the end, I said a little bit about these bubbles, which probably is not there in the universe, but knowing that they definitely don't exist will pretty much close all of this parameter space to the left of the QC axion line. So that's all I want to say. Thank you. Yeah. Huh? In which case? In the simulation that we ran? Yeah, we don't, because we don't have fermions. Like the thing that we started is the abelian Higgs model, right? So there's no BCS. We already done the BCS part. I'm just simulating the abelian Higgs model. Then yeah, there's no this thing. Yeah, like I don't include the fundamental fermion degree of freedom. Yeah. Yeah. So this one here. Yeah, so like in this region of parameter space, what happens is inside the sum, theta is equal to pi. So there are like a nuclear decays, like a beryllium to boron decay, which gives you neutrino lines. And if theta is not equal to 0, these neutrino energy will differ from the value that we measure. So coming from neutrino observations, for example, like there are many observations which tells you like the solar nuclear physics is happening at theta equal to 0. Huh? Yeah. Actually. Oh, like I think like for the neutral white dwarf, it doesn't really matter. Like all all you have like there is there's a scalar field, like the profile has a pressure, and this pressure is strong enough to push this thing in, and then the white dwarf will collapse. Yeah, so it's basically saying like in some region of the mass radius relation, the density is such that this object will either collapse or like evaporate. Like it's not part of the, like you remember, like so the mass relation, R relation that they have normally is something like this, right? Like and well, like theta equal to, like if you have this additional pressure term, you'll have this region and this region. And the reason is because like even you put some object in this region, it will collapse. Yeah. Yeah, it has nothing to do with theta. Yeah, yeah.
I would imagine that all the
No, I think like for example, like the deuterium is very sensitive to that. Like so, I haven't like really thought about like whether like 10⁻² or 10⁻³ is allowed, but I suspect it's somewhere around there. Yeah. 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 Huh? At high density, theta equal to pi in these regions. Yeah. High density. Because like so I can go through this equation. So basically like if you want to be living in this region of the parameter space where the particle is lighter than the QCD axion, then you are relying on some additional source of mass which cancels the mass that you are generating from the QCD. And that mass is always there, right? However, in this medium, like when the density increases, the QCD contribution goes away. And then like what you are left with is the opposite contribution that you put in by hand to like make the axion lighter. Yeah, it's not generic, but like for any axion which has a nucleon coupling, which lives to the left of this line, you are in trouble. This is a nuclear coupling. It doesn't work for the photon coupling. But like if you assume like this particle has a nuclear coupling, like the talk that we heard of in the morning, like how it changes nuclear physics, then like yeah, it will be subject to this constraint. Like just there, like we just talked about simple core collapse. But yeah, like but like there, like it changes very little, right? Like the proton neutron star, like the density, like the amount of like uncertainty in the density is like very tiny, especially if you take the square root, like in this log plot, it's pretty much like doesn't change like where the line is, like these uncertainties. Yeah. Yeah. I don't think that's the case. No. There are something like which some weird things which happens inside the domain wall. No, like there, like you would like so if you have a QCD axion like an axion domain wall at theta equal to pi, you will also get a pion domain wall there. But like at that particular point inside the domain wall, like there is a deconfinement, but like it's not generic. Yeah. Yeah, but like that region, like where like it is transiting theta equal to pi is very, very tiny, right? Like in the profile. Yeah. All right. Thank you.